Hi, physics. This is Mr. Janowski. Here are some videos from the Chapter 9 slides. So this is how you do a conservation of energy problem. So what have we got? We've got a 2 kilogram textbook, slides across the floor, eventually coming to a stop. If its initial velocity was 1.80 meters per second, how much work does friction do on the book? All right, so first thing, of course, grab your red pen. What are we looking for? We've got step, How much work does friction do on the book? So call that work F. Work of friction is equal to question mark. And what units will it have? Well, it's work, so it's going to have units of joules. On to step one. So step one, of course, is a sketch. And whenever you're doing any kind of conservation law, you should have two sketches. So we're going to have an initial sketch. And what's going on in the initial sketch? Well, we've got a floor. We've got a textbook. Ooh. All right, here's me trying to draw a textbook. So there's a textbook. It's moving. So it's going like that. We know the mass. That's 2.00 kilograms. Sorry, my writing looks pretty bad today. We know its initial velocity. V initial is 1.80 meters per second. And that's all that's happening. And then we're going to get to the final sketch. So in the final sketch, this is going to be really exciting. We've got a textbook, and it's not moving, which means V final is equal to 0 meters per second. So those are our two sketches, a book that's moving and then a book that's not moving. On to step two. Step two in a conservation of energy problem is to write the law of conservation of energy. This law right here. So sigma E initial, sum of your initial energy, plus sigma work external is equal to, let me make that more of a plus, is equal to sigma E final. So that is the law of conservation of energy, also known as the first law of thermodynamics. So what we're going to do is take this term by term. So sigma E initial. Well, look at your initial sketch and try to figure out what kinds of energies you have by asking the three questions. One, is it moving? Yes, it is moving. In the first sketch, it's moving, which means we have KE initial. Second question, is it at a height greater than 0? Well, we never talked about the height. This thing is not changing heights at all in this problem, so just call this height 0. So no, it's not at a height greater than 0, so there's no GPE. And then finally, is there a spring that is extended or blah, blah, blah? No, there's no spring at all. So sigma E initial, well, there's only one kind of energy. It is the initial kinetic energy. Plus sigma work external. Is there any external work being done? There is in this case. There's going to be work done by friction. So that's going to be plus W sub F, work done by friction. And this is equal to sigma E final. So look at your final sketch and ask yourself three questions. Is it moving? No, it's not moving. So that means there is no final kinetic energy. Is it at a height greater than 0? Nope, it's still at the same height. So GPE is still 0. And is there a spring that yada, yada, yada? No, there's no spring. So that means sigma E final is equal to 0. Simple. So the whole right side is equal to 0. On to step 3. Now, step 3 is math. Now, notice we're dealing with energy and work, both of which are scalars. So these guys aren't wearing hats, so we don't have to take off hats and worry about signs. The next thing we're just going to do is replace the things with the things, basically. Excuse me. So kinetic energy initial, well, that's going to be 1/2 m v initial squared plus work final. I'm sorry, plus work due to friction. Maybe I should go let W sub K. It looks like work final. No, but it's work due to friction. Um, maybe in a different kind of problem, you would replace it with this idea. FD cosine theta. But the thing we're actually looking for here is work due to friction. So we're not going to replace it with anything in this case. Plus work due to friction is equal to 0. All right, well, the thing we're trying to solve for again is this. So we're going to subtract the 1/2 mv initial squared from both sides. We're going to end up with work final is equal to minus 1/2 mv initial squared. All right, now put in the numbers. So minus 1/2. Mass is 2.00 kilograms. V initial is 1.80 meters per second squared. All right, so ask your calculator. Minus 0.5, 1/2, times 2.00 times 1.80 meters per second squared. Make sure that you're only squaring that last part. Oop. Sorry. I made a typo on the calculator. And if you do this, you're going to end up with work due to friction is equal to minus 3.24, and it's a work, so it's going to have units of joules. So you put a box around it. Then you grab your red pen. You do step, does this make sense? All right, well, first things first, we wanted work due to friction, units of joules. That's what we've got. So far, so good. And we have a small amount of negative work. Does it make sense that work can be negative? It does make sense because this is work being done by friction. And friction is always going to do negative work. Friction only takes energy out of your system. So it makes sense that friction does negative work. Negative 3.24 joules, that is a reasonable amount of work. So we're happy with that. We give it a check. So that's the first one. And I don't think that took too long. So I'm just going to make the other video. I'm just going to make one big, long, epic video with the other problem here. So here's another conservation of energy problem. We've got a spring with a spring constant of 325 newtons per meter. It is compressed downwards by 0.100 meters, and a 0.145 kilogram baseball is placed on top. How high will the ball go if the spring is released? So step one, what are we looking for? How high will the ball go? So what we're looking for is H final. And it's a height, so it's going to have units of meters. Now, of course, we do step one, which is make our two sketches. So initial sketch. Well, what have we got? We've got a spring. So there's our spring. We've got a baseball on top. Like that. So here's the baseball. Now, you know what? In for a penny, in for a pound. Have red seams. There we go. So there's our baseball. Now our spring is compressed by 0.10 meters. So what that means is if you let the spring just be itself, it would want to be at some higher point, but we've compressed it by this amount here. All right, so this is X initial. That is our initial compression of the spring. The spring by itself would want to be up at this height, but we've compressed it by that much. So X initial is 0.100 meters. The mass of the baseball, 0.145 kilograms. And this number, 325 newtons per meter, what is that? That's K. That's the spring constant. Let me squeeze it here next to the spring. So K is 325 newtons per meter. Now, that is just a number about this spring that tells you how strong it is. If it's a very strong spring and it takes a lot of effort to squeeze it or extend it, then it will have a high value for K. If it's a very weak spring, it'll have a low value for K. So anyhow, that's our initial sketch here. Let's point out one more thing. Is the baseball moving? Nope, at the beginning it's not moving. So V initial is 0 meters per second. All right, now for the final sketch. So we still have, there's the ground or whatever. Okay, the spring is now released. So the spring is up here. And the baseball will be at some height up in the air. All right, so what's going on here? All right, well, the mass of the baseball hasn't changed. How about the velocity of the baseball? Well, when the ball's at its highest point, it's actually not moving. So notice no speed lines. So V final is going to be 0 meters per second. Now, in between this point here and this point here, the ball was moving, but we don't care about what's happening, velocity in the middle of the problem. We just care about velocity initial and velocity final. So here, when it's at its highest point, V final is 0. How compressed is the spring? Well, at this point, the spring is released. So the spring is no longer compressed at all. So X final is 0 meters. No compression in the spring at all. Now, what height is this ball at? I should add that to the first one too. So let's call this H final. This is what we're looking at here. H final is question mark meters. I should have pointed out here in the first one that H initial, the height of the ball when it's at its lowest point, just always call your lowest point 0 in these problems. So H initial is 0. At the end of this problem, the ball is some higher height up in the air. So that's H final. That's question mark meters. On to step 2, which is write the law of conservation of energy. So sigma E initial plus sigma work external is equal to sigma E final. So sigma E initial, look at your initial sketch and try to figure out what kinds of energy you have by asking the 3 questions. 1, is it moving? No, it's not moving. So there's no kinetic energy. 2, is it at a height greater than 0? No. In the first sketch, it's at a height of 0. And then 3, is there a spring that is extended or compressed? There is in this problem. So what that means is we do have EPE initial. So we have one kind of energy in this initial one, in the initial sketch, and that is EPE, elastic potential energy. How about any external work? Well, we don't have any external work being done here. Now, the spring is going to do work on the ball, but that's internal work, basically. We're handling that as a form of potential energy, so that's internal work. And that's it. There's no friction or air resistance that we're worried about. So plus work external is going to be 0. Sometimes it'll be 0. It won't always be 0. All right, now let's look at the final sketch. And what kind of energies do we have? First of all, is it moving? It is not. No speed lines, V final is 0, so there's no final kinetic energy. Second question, is it at a height greater than 0? Yes, it is. So at the end of this, we are going to have GPE. So we've got a term for GPE final. And now the third question, is there a spring that is extended or compressed? Well, there's definitely a spring, but it is not extended or compressed. So there's no potential energy inside that spring. So there's no EPE. So that's all we've got. We've got EPE initial on the left side, and we've got GPE final on the right side. So one kind of energy on both sides. Now on to step 3, which is math. Again, these things are scalars. We don't have to worry about hats and signs and things like that. So we're just going to turn the things into the things. So EPE initial. What's your formula for EPE? Well, that's this guy right here. This is the one that students always have the hardest time remembering. But it's 1/2 K X initial squared. I'm going to specify that it's X initial because there are 2 extensions or compressions in this problem. So that's the left side. The right side, GPE final. Okay, well, here's your formula for GPE. So this is equal to mg H final. All right. Well, the thing we're looking for is H final. So we've got to get H final by itself on one side. So I'm going to do that by dividing both sides by mg. So divide both sides by mg. When you do that, M and G is going to cancel on the right. So we're left with just H final here on the right side, which is what we want. So now I'm going to rewrite this. I'm going to flip left and right because I would rather write it that way. And that's going to give me H final is equal to 1/2. You can put the half on the top if you want. It doesn't actually matter if you put it on the top or in the front. Times K. Well, what number is K? K is this number. 325 newtons per meter times X initial squared. X initial is this number. 0.100 meters squared. And then on the bottom, divided by the mass. Okay, mass is this. This is the mass of a baseball. I Googled it. At the time that I'm making this video, the Phillies are off to a great start. They're 4-0. So we've got that. And then G. Well, G is the acceleration due to gravity. Is it not on here? Oh, yeah, it is. There it is. Right there. 9.8 meters per second squared. So we've got to do this in the calculator. When you're doing this, make sure that you're getting your orders of operations right. Well, first of all, you want to make sure that you're only squaring just this term over here is one thing to do. And the other thing is you want to make sure that you're dividing by the entire denominator. So there are different ways to do that. One way to do that is to just throw on another pair of parentheses there. Yet another way to do that is just figure out what the whole top is worth. Write out some number for the top, figure out what the whole bottom is worth, write out some number for the bottom, and then do it again. Depending on how comfortable you are with the calculator, you'll do this in different ways. So I'm going to do 1/2 times 325 times 0.100. Then I'm hitting the x squared button. Now I'm hitting enter. So I've got a number for the top, 1.625. I'm going to write it in here. And forgive me for not doing the units here. 1.625. And then on the bottom, I'll just do the bottom separately. 0.145 times 9.8. And you get 1.421. All right, so your next step is going to be to divide 1.625 by 1.421. And you end up with 1.14356, yada, yada, yada. But if I keep 3 sig figs, I've got 1.14. And what units will it have? Well, it's a height. So it's going to have units of meters. So put a box around it, grab your red pen, do step We were looking for height final in units of meters. We have height final in units of meters. 1.14 meters, is that a reasonable height? Yeah, that's a little bit bigger than a meter stick. So hopefully you can imagine if you put a ball on a spring and pop it down and let it go, it might go about a meter high. So that makes sense. So that is our second conservation of energy problem. So hopefully this reminds you of things we've done earlier in the year. This is kind of a lot like last chapter when it was the conservation of momentum. There's more things to keep track of because there's, momentum is just P equals mv, whereas we have 3 different types of energy. But on the bright side, there are no hats, so you don't have to worry about the signs. So that makes things a little bit easier. So hopefully you found this helpful.